Okay, so let me, to give you some motivation about this research, let me start with the, COVID-19, which is our, common enemy. So this plot shows you the confirmed, active cases in Japan. So I don't remember when the first case was found. Maybe it was sometime in February. And so in the beginning, we were quite optimistic. And so that's why we didn't do a good job detecting the first wave. So I remember we got sort of, freaked out around, sometime in March, where, there was a, spread in, Italy and also New York City. And then, so what happened is, so it started to increase very rapidly. And, we had to, go through, basically the stay home, restrictions. So we basically got stuck at home in the month of April until, sometime in May. So probably thanks to what we did, so, this started to decrease. And so, this is where we are. Okay, so I want to point out, three things from this. And first is about the branching process. So this, curve is, basically something we expect for those of us who know about the stochastic processes. So the base is a branching process. And so in theory, if one person infects more than one person on average, then all right, so okay, let me. All right, so sorry about this. Okay, so the branching process says that if one person, infects more than one person on average, then it tends to increase exponentially. And on the other hand, if one person infects, less than one person on average, then it should, decrease exponentially, and eventually it's gonna die out. So there's one, important fact about the connection between the branching process and the Lévy process, so which is going to be the main theme of the talk. And thanks to the so-called, the Lampredi transform. And so next thing I want to point out is that, the optimal control, the decision makings under uncertainty is it's a very big thing here. So because of, what we went through, to decide to stay at home. So that's why, we could sort of, control the virus. I mean, at least at this stage. And at the same time, so this decision making is very difficult because basically the government has to, solve the trade-off between, minimizing, so saving, people's lives and also saving the economy. And what makes our life so much difficult is that, what we observe is far from being perfect. So there are, lots of noise about what we observe. And also, there are like lots of delays. So it takes about like 1 to 2 weeks since the time of the infection until, this person actually feels something. So let me talk a bit more about so these 3 points. And let me first talk about the CB process, which is continuous state branching process. And so this is essentially has a one-to-one mapping with the Lévy process. So what I say about, okay, so the continuous state branching process is okay, so the normal discrete state branching process takes only integer values. And if we allow this to take any positive real number, then this is going to be the CB process. And the CB process is the stochastic process. It's a strong Markov stochastic process, and which satisfies the so-called branching property. So this says that, so this is a population at time t, and the law of the population at time t, when it starts at x plus y, is same in distribution to the sum of two populations, one starting at x and the other starting at y. Okay, so this is called a branching property. So if we start with this, this decomposition, so we can show that, so this, random variable y has to be infinitely divisible, and its Laplace transform has to be written in terms of this form. So CB process is an example of a affine process. And so it can be written as exponential of minus x, which is a starting value of the process, and times so u. So this u is going to be the solution to this differential equations with this initial condition. And so this psi function, so it's going to be written in terms of this form. And so this is going to be nothing but the Laplace exponent of the Lévy process, whose jumps are always positive, which we call the spectrally positive Lévy process. So that's like one way to look at the connection between CB process and the Lévy process. And another way to look at is the time change. So if you start at a spectrally positive Lévy process x, and so if you apply a certain time change to this process in this way, where this time change is defined in this way, and then so the resulting time change process is going to be a CB process. And conversely, so you can start at the CB process and apply a certain time change. Then you get spectrally positive Lévy process with actually potential scaling. Okay, so let me move on to my second point, which is optimal control of epidemics. So this plot is something I kept seeing on TV when I got stuck at home. So basically, the government suggested us to, okay. So at that time, it was maybe April was here, and we didn't observe any information afterwards. And the government showed us this plot, and so we should aim at 80% of reduction of human contact. So if we can achieve 80%, what they said is that so the number has to first increase because of the delay of information, but then it's going to decrease very quickly towards zero. And they also show that if we only decrease by 70%, so it's gonna die out eventually, but it's going to be super slow. And what is bad is that so they said if we can only reduce it by 60%, then that's almost doing nothing. So it's going to keep increasing to infinity. Okay, so this decision making is quite difficult. So if we can achieve 80%, that's good, but that's going to be a huge impact on the economy. So here, in face of COVID-19, we have so many lots of control variables. So the government should decide if we should stay at home or even lockdown is necessary. And also, the detection of outbreak is going to be very important. So we didn't do a good job detecting the first wave. So that's why the virus is everywhere in every continent. And but we have to keep doing this. So for those countries which are stable now. People still have to detect the second wave. And for those countries which are in lockdown, then the decision to when to relax restrictions is going to be a huge important decisions. And there are other decision makings. And for example, the management of a number of patients in hospitals. So the capacity of medical resources such as beds and the ventilators are limited. So if the number of patients outnumber this capacity, then many people have to die. Okay, so the hospital has to decide on how many people to accept and so on. That's going to be a huge decision. And also the clinical trials of medications and vaccines are going to be super important from now. So we want to introduce new medications and vaccines as soon as possible, but we have to make sure that these are safe. So what makes so much difficult is that basically what we observe is not perfect. So this is mainly because this virus is new. And so in fact, okay, so what makes it difficult is that many people infected with the virus have no symptoms. So in the case of Japan, so this plot looks reasonable, but the actual number should be much higher. And so there are lots of delays. And so according to the website, this incubation period is believed to be about 1 week or 2. And there are lots of politics. What the government shows us, may have lots of noise. Okay, so motivated by this, so I'm going to talk about so basically 3 things. So the Lévy process is the main topic, and which has a close connection to the branching process. And in order to model imperfect information, so I'm going to talk. We're going to assume that instead of observing the process all the time, we're going to think about the case that so you can access to the information at exponential times. And also I want to talk about its application in the number of patients in hospitals. So this is one example of a scarce control problem. Okay, so now let me move on to the first part, which is the Lévy process. So so in this talk, so whenever you see X, so this is the Lévy process. So the Lévy process is so basically the continuous time version of the random walk, and it has 3 properties. First property said that the paths are right continuous with the left limits, and the second property says that the increments, the distribution of increments, is determined by the time interval. And the last requirement says that the increments are independent of the past information. So there are lots of important examples of the Lévy process. The Brownian motion is the most classical example, and so Poisson process is another classical example. And if you change the jump size 1 to some IID random variables, then this is called the compound Poisson process. And stable process is another important example. And so the Lévy process is often used in finance. So in finance, so typically, people focus on these processes, CGMY, temporal stable process. And the Barry's gamma process is a special case. And so normal inverse Gaussian processes. And if you take the sum of 2 independent Lévy processes, the sum is going to be Okay, so the summing is going to be again the Levy process. Okay, so some terminologies. And subordinator is a Levy process with monotone paths almost surely. And if I say expected negative, so this means that the jumps are always negative. And when I say expected positive, so this means the jumps are always positive. And let me remind you about the Lamperti transform. So this shows you the connection, one-to-one mapping between the continuously branching process and the expected positive Levy process. So when you talk about the Levy process, the Laplace exponent is always a good starting point. And so in this talk, whenever you see psi, so this is the Laplace exponent. So the Laplace exponent is the log of the Laplace transform of x at time 1, assuming that that's a 0. So by the way, I'm just focusing on the one-dimensional case. Okay, so so this Laplace exponent can be always decomposed into 3 parts. And the linear part corresponds to basically the drift. And the quadratic term corresponds to the Brownian motion. And this integral part is about jumps. So nu is called the Levy measure. So it may not be a finite measure. So it may blow up around 0. But if you take the second moment around 0, it has to be finite. And the one important fact about the Levy process is about its reflection. So let us define x bar t to be the running Spearman of this Levy process x. So this is basically means that it's a historical maximum of the path of x until time t. And in the same way, let me define x on the bar t to be the running infinite process of x. And so if you take the difference between the Levy process and its running Spearman process, then it's going to be a reflective process who's with the upper barrier, so 0. And in the same way, so if you take the difference between the Levy process and its running infinite process, then the difference is going to be the reflective process with a lower barrier 0. Okay, so these are for the cases when the barrier and the starting point are both 0. And if you want to differentiate these, some slight modification will do. Okay, so I'm going to talk about the fluctuation theory. I don't know the formal definition of this, but essentially we are interested in these quantities. Okay, the first is the first passage time. And so let tau a minus to be the first time the process x, the Levy process, goes below the level a for the first time. And in the same way, so let me define tau b plus to be the first time the Levy process x goes above b. Okay, so that's why. So this is the first passage times, and the resolvents are so given by this form. So this is essentially the distribution of x at independent exponential time, and also so overshoots are given by this form. So think about the event that the process goes above some barrier b, okay, and basically so this excess above b is going to so it's called the overshoots. And the undershoot is the difference between this barrier b and the position of x right before the jump. Okay, so let me talk about Wiener-Hopf factorization. So this is it's a very important the base of the theory of the Levy process. So remember, I define X bar to be the running experiment process, and X on the bar to be the running infinite process. So now let me introduce a random variable, which is exponentially distributed with parameters given by this Q, and it is independent of the Lévy process X. So what the Wiener-Hopf factorization states is that if you take the ratio between this Q and Q minus psi, remember psi is the Laplace exponent of the process X. So this ratio can be written as the product of two factors, which we call the Wiener-Hopf factors. So the guy with a positive sign is essentially the Laplace transform of the running experiment at independent exponential time. And in the same way, the guy with a negative sign is the Laplace transform of the running infimum at independent exponential time. So Wiener-Hopf factorization is very, very useful. But so unfortunately, not many examples are known where Wiener-Hopf factorization is explicit. But on the other hand, there are some examples. And spectral negative Lévy process is like one example where Wiener-Hopf factorization is known. So remember, spectral negative Lévy process is a Lévy process with only negative jumps. And so it's, okay, so the Laplace exponent. So the only thing we have to modify is that because it only jumps downwards, so the support of the Lévy measure has to be the negative half line. Okay, so everything else is the same. So if we focus on the case of a spectral negative Lévy process, so you have, for example, this. Okay, so for the case of a spectral negative Lévy process, so this random variable, which is a running experiment at the exponential time, independent exponential time, is in fact exponentially distributed, whose parameter is given by this capital phi, and which is the largest solution to the equality that this psi or the Laplace exponent equals this Q. Okay. Now remember about the Wiener-Hopf factorization. Okay, so this guy is the same as this guy, and we also know how to compute the Laplace transform of a exponential random variable. So we have basically we can compute one of the factor, and thanks to the Wiener-Hopf factorization, okay, so we have this the Laplace exponent. We know one of the factors, so we can compute the others, which is given here. Okay, so that explains why assuming spectral negative Lévy process makes our life much easier. But there are some other reasons. So this is because of the scale functions. So the scale function is defined for every spectral negative Lévy process, and so I'm going to use WQ and for this, and Q is basically the same Q you saw before. So this is sort of like a discount in finance. If you don't like finance, so this can be seen as a killing rate. So the scale function is a mapping from a real number to a positive real number. And so it's essentially defined by the Laplace transform. So if you take the Laplace transform on the positive half line, then it is going to be given by 1 divided by psi, which was the Laplace exponent, minus the scaling rate Q. And this holds for every large enough beta, which is bigger than this phi. So this is the same guy you saw And again, so this is the logic solution to the equality that the Laplace exponent equals the scaling rate to. So so this essentially defines W on the positive half line. And but it's not so important, but it's customary to extend the domain to a whole real line by just assuming this to be 0 on the negative half line. Okay, so what can we do with the scale functions? The first application is about the first, passage time. So remember that I define, tau A minus to be the first time this process X goes below A. And tau B plus is the first time this process goes above B. So if you think about the event that, it goes above B before going below 0, and if you apply some killing and take expectation, then so this can be written as a, the ratio between the same scale function at, different values. And you can also compute for the other event that it goes below 0 before going above B, and you apply scaling and take the expectation. So remember, we are assuming X is a spectral negative Lévy process, which is very, very asymmetric. So this time it's going to be a bit more complicated, but this Z guy is given by 1 plus Q times the integral of W. So once you know W, you can compute Z, and we have the expression. And another application of the scale function is about its applications in the reflective process. So remember that so if you take the difference between the Lévy process and its running Spearman process, so then the difference is going to be the reflective process. And if you want to think about the case that when the starting point and the barrier are different, so we have to shift a little bit. So if you take the difference between the running Spearman and A, it's going to be the barrier. Okay, and then you take the maximum between, so this difference and 0. Okay, so that is going to be L. So if you take the difference now between the original process X and this modified running Spearman, then so this remaining guy is going to be the reflective process with upper barrier A, so whose path is like this. Okay, so now so let me define some stopping time, nu A. So this is given by the first time this process, this reflective process goes below 0 for the first time. And then you can, for example, compute these quantities. So this is essentially this discounted amount of reflection accumulated until the first time this reflective process goes below 0. So then so this can be written nicely in terms of, again, the scale function. And so this is given by W divided by so W prime. And yeah, so that's one application for the reflective process. Okay, so now so let me move on to the second part, which is the Lévy processes observed at the Poisson arrival times. Okay, so I'm going to keep using X for the Lévy process. So now I'm going to introduce a new process, N lambda, which is a Poisson process whose intensity is given by lambda, and it is independent of the Lévy process X. And now we are going to think about the situation. So instead of assuming that this process X, the Lévy process, can be observed all the time, now we are going to think about the scenario where the Lévy process X can be only observed at the jump times of this Poisson process given by ti. Okay, so this is going to be the sequence of information. Okay, so in other words, you always have to wait for independent exponential time until the next observation. Okay, so it's a very simple scenario. So what I want to discuss here is about the Poisson version of the fluctuation identities, which I reviewed in the first part. Okay, so remember that so tau 0 minus is so what I call the classical first passage time. So this is the first time when this process x goes below 0. So in this simulation, for example, let's say 0 is here. And so this is going to be the first time. So this process crosses the level 0. Okay, so here it's going to be maybe some where around here. So this is going to be what I call the classical first passage time. And now, so I want to I want to introduce its Poisson version. Okay, so we don't have a formal name for this, but let me just call this Poisson first passage time. Okay, so if I put the hat sign, so this is going to be the Poisson first passage time, which is essentially the first Poisson observation time at which the process is below 0. Okay, so in this plot, so for example, so this is the first observation time, which is given by T1. Okay, you observe the process that is still above 0. Okay, let's wait for the next observation time. Okay, again, it is above. So let's wait for the next observation time. And again, it's above. Okay, so let's wait again. And finally, you find the process to be 0. Okay, so this time is going to be what I mean by the Poisson first passage time. So, in order to somehow connect between these two, let me remind you about the Wiener-Hopf factorization again. So Wiener-Hopf factorization is about two random variables: the running experiment at the exponential time and the running infimum at the exponential time. But in fact, this version of the Wiener-Hopf factorization is the simplest version. And the more general version actually deals with 4 random variables: this guy, and this guy, and this guy. Okay, so this G guy is defined here. So GT bar is given by, so basically the last time of max before time t. So this is the last time before t where the maximum was updated. And in the same way, we define G underbar t to be the last time of minimum before time t. Now, so we just replace t by independent exponential random variable, lambda t. And the general Wiener-Hopf factors are given by, so these, Wiener-Hopf factors. So these are the Laplace transform of so G bar at independent exponential time, and the running maximum at independent exponential time. Okay, and same for this minimum guy. Okay, so these are not always computable, but so there's a very interesting observation by Albrecht and Ivanovs, and so they talk about the connection between the the Poisson first passage time and the classical first passage time. So which states like this. So if you take the joint Laplace transform of the Poisson first passage time and the position of x of this time. And so this is connected to the classical first passage time and the position of x, the first classical first passage time. It's linked in this way. Okay, so it's still a bit complicated because it still requires some random variables, which is given by here and here. Okay, so these are basically independent copies of the ones appeared in the Wiener-Hopf factorizations. Okay, so if we can compute about so these guys, so then we can obtain the joint Laplace transform of this Poisson first passage time and the position at the time. Okay, so again, so let me cheat, and so if we can if we assume again the spectral negative case, or the case when there are only negative jumps, then so everything is computable. Okay, so the Poisson first down crossing time. Okay, and so we can basically obtain the joint Laplace transform of this first Poisson first down crossing time, and the position of x that time can be computed in terms of the scale functions. So I didn't define these functions, but this can be derived by the scale function w. And in the same way, if you define tau hat b plus to be the first Poisson up crossing time, then we can obtain the joint Laplace transform of this time and the position at the time in terms of, again, scale functions. Okay, so now let me talk about the Poisson version of the reflection. So remember, the classical reflection is easy because you can only take the difference between the Lévy process and it's running Spearman process. And we want to come up with the Poisson version. So in the Poisson case, we can't quite do this because we only observe the process at times. And what I mean by the Poisson, reflection is that, so basically we try to do, the same as much as possible, but it's going to be like this. So set some barrier, let's say B, and at each Poisson observation time, and if the process is above the level, then you just push the process down to the barrier B. Okay, so you just keep repeating this fashion. So the resulting process is going to be, what I call the Poisson reflective process. So I don't know the best way to write, but it's basically the difference between the original process X, and L is the sum of these red arrows before time t. Okay, and in fact, so we can do a lot with this process. Okay, so let us define this stopping time to be the first time this Poisson first Poisson reflective process goes below 0. Then we can obtain some quantities like this. So this is a discounted amount of a reflection, Poisson reflection accumulated until the first time this reflective process goes below 0. So this can be again returned in terms of the scale functions. All right, so now, so in the remaining 5, I don't know how much time I have, but 5 to 10 minutes, let me talk about the stochastic control. Okay, the story is something I described in the beginning of the talk. So imagine, so there's a hospital, and so the number of patients follow some, the Lévy process X. And so basically, So the hospital has to reduce the number of patients, sometimes in an undesirable way. So this is because if there are too many patients in hospital, because the capacity of a medical resources are limited. Okay, so so this may lead to the collapse of healthcare. And also, if there are too many patients, the risk of in hospital infection is going to increase. So now, so the hospital has to make a decision to reduce the number of patients in a costly and undesirable way. Okay, so for example, by so refusing new patients, just saying, okay, we are full, please go to a different hospital. And another way is, for example, the use of risky medication, which may have potential side effects. And also, so this is something happened in Japan. So relocation of patients to other hospitals or hotels for those patients who have mild symptoms were sent to hotels to focus on patients who really need care. Okay, so now so we want to find this policy R. Okay, so we want to find this stochastic process R, and so if you apply this strategy or the policy, so then the difference is going to be the controlled number of patients, so which is given by U pi. Okay. So what we want to do is to find the best policy strategy R, so as to minimize so this cost. Okay. So this cost consists of two parts. The first part is a running cost, and second part is a controlling cost. Okay, so this is derived by this function f. So imagine some function which first decreases and increases. So you don't want to have too many patients in the hospital, but you don't want to have too little patients because they still have to make money. And also this controlling cost, we assume that so this is proportional to the amount of R. Okay, so the proportional to the amount of a reduction. And so this C is a constant. Okay, so the problem is to find the best policy R so as to minimize so this expectation. So this R, the strategy, has to be adapted to the filtration of X. And also it has to be increasing because this is an aggregate number, so it can never decrease. And for technicality, we're going to assume that this is a Cadillac. So this is a very classical, stochastic control problem. And many people have succeeded in, showing the optimality of the barrier strategy. So basically, you set up a cap B star and accept, okay, to reduce so that the number is never going to go up above B star. Okay, so which means that what I mean by the reflection strategy is going to be optimal. So now we are going to think of the Poisson case. So now, instead of assuming that so you can reduce the number at all times, instead we can do so only at exponential times. Okay, so again, so this is basically the same thing. So n lambda is an independent Poisson process. And so jump times are given by Ti. So you can only activate, only increase R, only at the jump time of n. So your strategy has to have this form. Okay. And for math to make sense, so this density has to be a predictable process. Okay, so everything else is the same. So we want to again minimize the sum of running cost and the controlling cost. The only difference is that we restrict the set of policies, strategies, which takes this form. Okay, so you can only reduce only the times of the Poisson arrival times. Okay, so so we can show, we could show that for the case when x is a spectral pulse, Levy pulses, and so the convexity of f is something commonly assumed, and we have to assume a few conditions so that everything is going to be integrable. Okay, so as you can imagine, that what we try to show is that, so in this case, so remember in the classical case, the classical reflection strategy was optimal. So in this Poisson case, so the Poisson reflection strategy should be optimal. So basically for some barrier B star, and what you should do is to each time you observe, which time you have opportunity to reduce, whenever you observe the number of patients to be higher than this cap, then just decrease the value to this barrier B star and keep doing that. And this B star can be written as unique solution to some equality. And in stochastic control, so we have to show the optimality of this candidate strategy by showing the verification lemma. So this essentially reduces to showing the the variation inequalities. Okay, so not much in detail, but the conclusion is that so basically this Poisson reflection strategy is optimal. Okay, so that's all I wanted to say, and so I put some slides. I put some literature papers for your reference, and I don't have time to go through, but I put this slide on the website. Okay, so that's my website, and so if you go to this, so you can have access to the slide. And also, if you have questions and comments, feel free to write me email. Okay, so thank you very much for your attention.